Okay, this is a test of Building Services 1 lecture. We'll use English for the first time. I'm Craig Farnham. Let's start. So this is lecture 1, part A, 1A, background for ventilation, which is an important topic. Today we are worried about closed spaces with poor ventilation, which is a contagion risk as announced by the Japanese government. So, as building engineers, we need to know exactly what is poor ventilation. But first we need background. So, the first step is to know about the key in kanki, which is kuki, air. Air is heavy. A cubic meter of water, you know, is heavy. It weighs 1,000 kilograms. A cubic meter of air weighs 1.2 kilograms. We don't feel the weight of air because the pressure on our bodies and from inside our bodies is equal. But the ventilation system does feel the weight of the air. But what is air made of? You all know it's nitrogen, oxygen, a little bit of argon. For our work, we're going to talk about CO2 a lot. Normal air has about 0.04% CO2. There's also other things like neon and helium. These percents are for dry air, not including humidity. Humidity changes, so actually the amount of water in the air is anywhere from 0 to 4%, which changes everything. We'll also talk about pressure a little bit later. You all know pressure is a force on a unit area, but for us the important thing is knowing about atmospheric pressure. To start, the standard atmospheric pressure, maybe you notice from seeing a weather map, it's about 1,000 here, and those units are hectopascals, 1,000 hectopascals, so just pascals is 101,000 pascals on average, or about 1,000 hectopascals, or 0.1 megapascals, which we measure with a pressure gauge. A pressure gauge normally shows 0 in the air, but really the air pressure is always about 100,000 pascals. So when we talk about pressure or measure pressure, there are two different pressures. Gauge pressure, which shows on a pressure gauge, which is usually at 0 in our atmosphere. And absolute pressure, which includes the standard atmospheric pressure. So when you check your tires, we don't know this part. We just get the extra on the gauge. So for example, a tire might want 35 to 65 psi. What does that mean? In America, psi is still common. 14.7 psi is the same as this, 100,000 pascals. The reason for ventilation is to get rid of indoor air pollution, to take dirty air and replace with fresh air. There are many things inside a building that release bad gases, things you don't like, things in the kitchen, smoke and combustion gases, breath, sweat from people. Also, there's heat, of course, from a toilet or steam from a shower. So, in this field, we talk a lot about indoor air quality. Is the air in a room nice or not? And there are, as we said, many things in a building which release things that become poor air quality, like VOCs, volatile organic compounds, dust from your skin and from your clothes, carbon dioxides, nitrogen oxides, sulfur oxides, etc. Even droplets of water from sneezing and coughing, or smoke, or smells, or the humidity and CO2, etc. all become higher and higher when people are using a room. So, all of these bad things in the air, we want to vent them out, and that means we need fresh air. If we don't ventilate all of those bad things out, a common problem is sick house syndrome or sick building syndrome. Many people might feel tired or even dizzy, eyes and nose irritation, in bad cases headaches, feeling nauseous, etc. There are two main ways to do ventilation: the natural ventilation and mechanical ventilation. Natural uses wind and windows and differences in temperature to help move air through a building. Mechanical, of course, uses fans. Natural ventilation is, well, free. It uses no energy, but it's not stable. Sometimes there's not enough ventilation, and you might need to do special designs of your building to do this. Mechanical is stable and easy to control as you want. You can get a lot of ventilation. It's very easy to create ventilation for many situations, but you have to calculate exactly what kind of fan you use. But the big and negative point is you need to use a lot of electricity to do it. Back in the 1970s and 1980s, for saving energy, many buildings tried to shut the windows and reduce the ventilation, because ventilation takes a lot of energy. But the result was sick building syndrome. Many people felt dizzy or sick or had allergies, etc. So we need to have enough ventilation to prevent this. CO2 is 1000 ppm. Some of you, I'm sure, know what a ppm is, but it's important for our calculation. So what is a ppm? It's kind of like a percent. A percent, you already know, is originally from Latin, then French into English, per cent. And cent is cent from French, which means 100. So per 100. ppm is English parts per million, or 100 manbun no ichi. It's 1 ppm. So in percents, 1 ppm is 0.0001%. More easy is 10,000 ppm is 1%, and a million ppm becomes 100%. For small amounts, for the standards, ppm is easier to understand than trying to do 0.000%. There's also ppb and ppt. So, what is the CO2 concentration and what does it affect on the body? In air, the CO2 ppm is usually about 400. In a building, the first limit for our general indoors is 1000. Or if you do proper calculations, you can do 1500. If the CO2 in a room goes above 2000, a few people might start to feel a little bit unwell. Between 2000 and 5000, more and more people will maybe feel tired, maybe feel even a little dizzy or get a headache. Some people might even feel nauseous. 5000 is generally the high limit in many international standards, especially for factories and workplaces. You can't go over 5,000, and you shouldn't go over 1,500 for a common space, or even 1,000. Over 5,000, it starts to get much worse. Almost everybody will feel sick, and then when you get to 10,000, 20,000, 40,000 ppm, you have trouble breathing. At 80,000 ppm, which is 8%. Over 10 minutes, you start to do damage to the body, and 16% is deadly. A famous case of CO2 going too high was the Apollo 13 accident. In the ship, a tank blew up, and they couldn't use their CO2 filters, and the CO2 level inside the spaceship became 20,000 ppm, which is 2%. In space, you can't do ventilation, so they had to make a special new CO2 filter by hand with duct tape. So for us in buildings, usually we're worried about CO2 from breathing. So how much CO2 does a person make? So generally, one person breathing makes, when they're resting or doing very low activity, somewhere from 0.25 to 0.35 liters of CO2 every minute. If you're sleeping, your metabolism is lower. If you're working or doing light exercise, you might make 3 or 4 times as much CO2. If you're doing really strong, heavy work or strong exercise, you might make 4 or even 6 liters of CO2 per minute. The feeling is that if you're designing for people, if you can ventilate enough to get rid of the CO2 in a room, you're probably also ventilating enough for all the other small amounts of gases like VOCs or like formaldehyde or carbon monoxide, etc. But of course, you need to check that with a building engineer. So that's just the first part. This is a test run of part 1A of the first lecture, and we'll go to part 1B.